In mobile application security, good enough is a vulnerability. GuardSquare delivers the highest level of security for your mobile apps without compromise. Discover how GuardSquare provides industry-leading security for your Android and iOS apps at guardsquare.com.
Hi everyone, my name is Srini Pinchikala. I serve as the lead editor for AI, ML and data engineering community at the InfoQ website, and I also host podcast episodes. In today's episode, I will be speaking with Somtochi Onyekwere, software engineer at Fly.io organization. We will discuss the recent developments in distributed data systems, especially topics like eventual consistency and how to achieve fast, eventually consistent replication across distributed nodes. We'll also talk about the conflict-free replicated data type data structures, also known as the CRDTs, and how they can help with conflict resolution when managing data in distributed data storage systems. Hi, Somtochi. Thank you for joining me today. Can you introduce yourself and tell our listeners about your career and what areas have you been focusing on recently?
I'm glad for the opportunity to be on the podcast. Thank you, Srini. So like you said, my name is Somtochi. I'm a software engineer at Fly.io, where I work primarily on Corrosion, which is our open source distributed system. And I'm also on the networking team because Corrosion powers our networking stack. So basically distributed systems and networking software. Fly is a cloud startup for deploying your applications. Before Fly, I worked at a company called Weaveworks. One way or the other throughout my career, I've worked on some form of open source software, but it was primarily for building open source controllers for Kubernetes that helped users deploy their applications through GitOps, which is like managing deployment through files stored on Git. So one way or the other, I've been involved in developer tooling, deployment, infrastructure. Also part of the Kubernetes community just from way back, from even way before my career, where I did Google some of code. So I've mostly been working on Kubernetes, distributed system, infra. So that's mostly about that.
Thank you. Yeah, that's a lot of different areas of expertise. I'm definitely very curious about Corrosion framework. I know how it works and everything. So maybe we can start with kind of more high level topics on that framework. So one of the goals of your project was to be able to write data on one server node and read it from other server nodes without much delay, without much latency. So can you talk about how you are able to achieve this? What kind of patterns and practices that you and your team implemented to achieve these goals?
Yeah, sure. So normally, when a machine is created on Fly, we want to do that quickly. We provide a system where you can deploy applications anywhere. So when people will create machines, create VMs, they expect to be able to reach it pretty quickly. So we favor speed over consistency. And this has also shown up in how we build software, right? Because if you're trying to make everything consistent, making sure that everybody agrees before you move ahead, you're going to have some trade-off in terms of latency. Before Corrosion, we used to use Console, which is strongly consistent, uses Raft for consensus. So before that, we used Console and we created sort of Corrosion out of a problem. And that was basically, we just wanted data at different points very fast. So already the problem that we're creating Corrosion for had to do with speed. We are pulling console servers at first, pulling the API, trying to insert it into data and into a JSON and have that everywhere, have the software read from that. But that didn't really scale well, trying to pull the API X amount of times. So we've seen that a lot of times, not just in Corrosion, but in other software that we use, where we don't necessarily want to make the best case decision, but we want to make a decision quickly. We want access to information to be able to make a decision quickly. So that has played out, especially in Corrosion, where it's a very relaxed system, is eventually consistent, and it's fast.
That's where the whole CAP theorem comes from, right? The consistency, availability, and partition tolerance. So can you talk about the application use cases and discuss how the eventual consistency did not affect the quality of the data?
The thing is, of course, there's going to be systems that need to be strongly consistent, right? If you're using a bank, right, you don't want eventual consistency, right? It could come up in many funky ways. But for a vast majority of internet applications, eventually consistency works when you relax the consistency guarantees, right? You're like, okay, this data might be a little out of stale, and maybe I might make a suboptimal decision, but I get to do that quickly.
Yeah, with the eventual consistency, how do you ensure the data quality of the application and that there are no issues?
How we ensure the quality of the applications and there are no issues is that we have a system that handles it, right? We have ways of dealing with stale data within the system because most times it's the two things with eventual consistency. It's either all the data is arriving too late or there's two different parts of the platform writing to the same place. And it's like, okay, what's going to win? Which wins, right? So with stale data, it's just finding a way to make good decisions, even if the data might be out of stale. For example, our networking software now, when a request comes in for a machine, so we have servers called edges. So all the requests coming through edges, and then the edges routes the request to the right worker. If a request comes into an edge, it matches like the IP to a particular machine and it picks a machine, but maybe that machine has been deleted, but it doesn't know that yet. It's like, okay, this machine is started. It's going to send the request to a worker, which are the actual VMs that run the machine. So it's the one updating the machine state. It has the most recent state, definitely, because locally, if it writes to, say, corrosion, it gets the readback. So corrosion on the worker has the most recent state. So when the edge sends the request to the worker and it's like, okay, send this request to a machine on there, it can send a response back to the edge saying, oh, this instance actually has been deleted or wasn't found. So the proxy now reroutes it to another machine. So this is just like a small example of how to deal with stale states. Even if the state is a little out of date, maybe you route it to a closer machine, a closer server that has the closest state and have it respond back with, okay, this is not right. Or if it is right, it will just, do the right thing with the request. In this case, it will write it to the right VM. The other one is conflict resolution, which is like different things writing to the same data. So we have a means of conflict resolution within the system. But even above that is that sometimes your data is even structured in a way that you don't really need to worry about conflicts, right? Like we have different servers and each of those servers have a particular set of machines. It's all in the same table, right? We have like a table that contains the machine's data in SQL, but each server writes just for its own. So basically each row kind of has an owner because each server just writes for the machine that it is in charge of. So even though, it's a distributed system, there are multiple things writing to the same table, there's actually not a lot of conflicts because there are different things that own different parts and different roles in the database. So just little things like that where you just adjust your system a little bit to be able to work, relax the consistency constraint that you require from your databases or your storage systems, in able to gain some speed and still be able to work efficiently.
You have used conflict-free replicated data types, CRDTs, right? They're called to handle some of these requirements. Can you talk about these specialized data structures? How do they help with the conflict resolution? How can we use them in other applications?
Sure. CRDTs, like conflict-free replicated data types, I feel like they've been around for a while in like the distributed system community, but it's like they're having a comeback now with just more research being used in more software just because of how they allow people build eventually consistent systems and resolve conflicts in them. So CRDTs is mostly a concept around data types and possibly associated algorithms where you have independent replicas able to accept writes and update the data without communicating with each other. So each replica can accept writes. And then those replicas at different time, doesn't have to be a long time, can exchange the data they have. And then part of CRDT is like when they exchange the data, they converge to the same state. So there's some background mechanism, some algorithm that probably runs when the data is exchanged that would ensure that regardless of the order in which the replicas have received the changes, they converge to the same states. So there are different ways and different data types that have been brought up. I feel like a very popular example, which can make it easy for someone to grasp it, is like, let's say, a replicated counter. And so in CRDTs, there are mostly two types of CRDTs, where you have state-based CRDTs. So in state-based CRDTs, the nodes exchange all of their states between each other, and they find a way to merge to different states. And then you have an operation-based CRDT, where they exchange the operations that they have received instead of the whole states. Each approach has their disadvantages and advantages. Of course, if you're exchanging the whole states, you're going to have way more network communications, but it means that there's less guarantees. If you're communicating operations, it means you have to be more careful in terms of duplicates and stuff like that. For something like a replicated counter, so I'll give a state-based example and an operation-based example. So for a state-based example of a replicated counter, say you have a counter, two different nodes, they get updated, incremented separately. Maybe one is incremented twice from 0 to 2, and the other one is incremented once. So one has the value of 1, the other one has the value of 2. When they exchange their states, your merging function can just be one that takes a max. So in this case, it'd be like a grow-only counter, right? So if your counter can only increment, a good example is like maybe likes on like an Instagram post, because, okay, you can unlike, but let's say an Instagram post that you can't unlike, so it's a grow-only counter. So in that case, when you exchange the two states, you just know that the merge is just going to take the max of the two functions. And you know that regardless of whatever order that you exchange state between different counters, you still get to the same stage. But for something like an operation-based CRDT, they exchange operations. So in this case, one will send like the 2 increments it has received to another node, while the other one will just send the other one. Operation-based CRDTs don't have as much network requirements, but it means that you need to be more careful, about, say, duplicator states, because let's say there's a network issue. I don't know if the other node has received it, and I send the increment counter again. It might increment it more than required. So there are many ways to work around this, maybe some versioning so that they can discard an already applied version kind of thing. But basically, if the two counters exchange the exact number of operations that they have gone through, they would come to the same state. So I think this is a very good example of, this is a simple data structure that people interact with daily, and this is how it can easily be kind of a CRDT.
Right. So other than the Instagram counter, right, are there any other examples, like other business use cases?
Yeah, the counter is, of course, very simplified, but just easy to understand. So you have something like grow only sets. So a set is nice in that you can't get duplicates. So once you add something to the set, it's been added, right? But you also have to now deal with concurrent additions and removals. So some sets have something like an add wins, depending on what the set is being used for. It might be a case, so it's where the business logic now comes into play. Some sets are like, once there's an add, there's a concurrent add and remove. The add always wins, which is just static. There's also remove wins set too. There's also like an observed remove, where each add and each remove, there's some data to track what's been added and what's been removed. You don't just have an arbitrary operation wins, but whichever operation has been done more times win. There's also like CRDTs that use the concept of last writer wins, which is they find some way to track timestamps on operations. So whichever one has the older timestamps win. Of course, there's some trickiness to this, because when you're working with distributed systems, you can't depend on system time. So you have to start thinking of something like Lampworth's clock to track the timestamps. Yes, there are also like some data structures that kind of leave it up to the application to decide on how best to resolve the conflict too. So it keeps conflicting. It merges, the changes. Git is a good example actually, because Git would merge whatever changes it can and then tell you, I can't manage this. There's a conflict here that I can't really understand. So there are some systems, they will merge as much as they can without conflicts. But when there's a conflicting, they might leave it up to the application to decide.
Also, on a similar topic, in your presentation at QCon conference earlier this year, you mentioned the order of data changes shouldn't matter. So for the counters, It makes sense. But how do you handle the data changes that come in at different times or other use cases where they're a little bit more complex than just a counter example?
The main thing is whatever order the changes come in, the two replicas should converge to the same state. So there's that consistency. As much as is an eventual consistency, is a strong eventual consistency. Whatever algorithm people have, when you have a different order, they should eventually decide on the same state. The main thing is understanding, the algorithm behind whatever CRDT you're using is. Let's say something like you're breaking ties on the timestamp, right? It has to mean that each person is breaking ties all the time. If someone is breaking ties early different the value, it becomes trickier, or they are not storing the right timestamp. So let's say it receives a change, right, that has a greater timestamp, but it doesn't store it. So it takes the value, but not the timestamp. If another change comes in that maybe it has a smaller timestamp and it's not supposed to be, because it still has an older timestamp, it gets out of sync. So basically how the nodes accept and resolve conflict, the order of changes should not matter. So even if, let's say, it's breaking a tie on the node, like an ID, right? The comparison, the way it compares and lands on which of these changes win should be the same at every replica. So that even though it might not be what you expect, but that it's going to be the same data everywhere, as long as each of those replicas have communicated with each other.
Makes sense. So regarding the CRDTs, right? So just kind of get back to that. Are there any limitations, like when they're not good candidates to use in applications?
I think, sure, there are definitely limitations to CRDTs. Most times come with associated metadata that helps in conflict resolution, especially the not so simple ones. For the observed removed set, it has like a second set tracking, like what they call tombstones, which is like the number of times an element have been separated or removed. So if, depending on the CRDTs, if you're working on a very space-constrained environment, you can't have this additional thing storing extra data. It depends on the CRDT you're working with. So if it's a CRDT where it has an excess metadata or there's an extra garbage collection that is happening in the background, it might not work for you. If you care about the order of changes that you receive, basically you have like the type of data you're managing is serialized. So if you write a 2 and then you write a 5, you'd never want the 5 appearing before a 2. That could happen in CRDTs because they do not track the order of changes, right? It's like if a 5 comes in first, it would show you a 5. So in those kind of cases where the order matters, you want strong consistency, because a lot of times CRDTs are used in virtually consistent systems. That's something to consider. Maybe you need something more, maybe your data is more complex and you can't find a type of CRDT that will let you define a conflict resolution, right? Some CRDTs, they come with already how they manage conflicts, but maybe you want to manage it differently. Maybe instead of choosing the one with the biggest timestamp, you want the one with the bigger value in that kind of way. They're just little things that you need to consider when you're trying to pick up CRDTs. But the main thing you need to think about is like, how do they resolve conflicts? Am I okay with that? Am I okay with the concept of CRDTs and what it means for my application, meaning that rights might appear out of order? It might be a bit before all the changes quizzes because, you have network partitions. Do you understand how it works under that? So just little things like this, I think those considerations might be a limitation for applications here.
I also want to talk about the topic of data replication. The corrosion framework replicates SQL data across the nodes. So can you talk about, eventual consistency makes sense to bring all the nodes up to date with the data changes? But, how does the data replicate between the nodes?
Corrosion is the system that we built at Fly to replicate SQLite data to like a global cluster. It's eventually consistent using CRDTs. So as soon as you write, you'd respond almost immediately, but it would not be immediately available at all the global clusters. Part of what we try to do with corrosion is ensure that it is quickly available. We try to keep the communication quick. Part of how we do this is that we use a gossip protocol. When you make the change, we broadcast that change to all the closest nodes. I think part of this is just that data is more likely to be read close to where it's written, right? It's just that locality associated with most data. Doesn't always happen in all rights. But first of all, we broadcast it to all local nodes. And then we do a gossip-based dissemination to the rest of the cluster. which is sort of this kind of epidemic protocol where one node sends to 8 nodes, and those 8 nodes send to 8 other nodes, and the change kind of spreads exponentially across the cross cluster. But the broadcast is kind of fire and go. So it's possible maybe a node is down, didn't receive the broadcast, it missed it in this time. And what happens then is that we also have the periodic sync protocols that run where, a node contacts other nodes, they exchange states, and the node contacting is able to find out which version is missing. We attach version numbers to each change that comes into corrosion for like state tracking. So when it contacts the other nodes and they exchange some data, it's able to know, oh, I'm missing this version, so these are called gaps in corrosion. It has these gaps, and then it's able to request from those gaps from those nodes. So this sync protocol runs periodically. So even if a node misses a broadcast or doesn't get broadcast too quickly enough, the sync protocol will also make sure that it's communicating with these other nodes and is able to exchange any states that is missing. Another thing we do within corrosion is like we also favor like more recent states in when we are processing data. Let's say with the sync protocol where we request data from other nodes, we request the most recent data first, just because it might have been overridden with more recent one, right? Just little things like that, little decisions that we've made within corrosion to ensure that it's very quick and it's able to replicate data very quickly.
Also, you mentioned about local nodes, they get the data faster, and the global nodes may take some time. So can you share some statistics on this? Like what is the response time for local nodes? Is it like seconds or milliseconds?
Oh yeah, the local nodes is definitely milliseconds. It's pretty short. It's almost the same thing as writing to an SQLite database. It would write the changes to SQLite and return immediately. So it's order of milliseconds. But for the global cluster, we have like a P99 of about 1 to 2 seconds. Yeah, so it's pretty quick. In 1 second is enough that before someone tries to read the data, most times it's already there. Or like I said, retries, right? That's also another thing to do with eventually consistent data. Sometimes you receive a request, maybe for a particular machine or something, and this data is supposed to be there, but it's just not there right now. You can easily implement your retries. If the system replicates data under 2 seconds, you can have a 2-second retry. Like if it's not then there, probably a node is lagging somewhere, or, there's just something.
So eventual consistency doesn't have to be that long, right? It can be just in a few seconds.
Yeah, it doesn't have to be very long.
So this framework, can you talk about the technology stack behind it? It definitely does a lot of great stuff. So what is it built on?
Yeah, it's written in Rust. Rust is just a good language for this kind of systems where you are aiming for speed and safety at the same time, right? It has to do with data. We don't want random crashes. We don't want random garbage collection happening as maybe the system only supports a bit. So Rust is good in that way. It's type safe, zero cost abstractions, little things like this. So a lot of things we use are within the Rust ecosystem. We use the Tokyo, which is very popular async runtime that Rust uses. Rust project. Tokyo comes like with a host of utilities like the channels for communications, mostly Tokyo channels. So basically we write a lot of async code within corrosion that's used a lot. A lot of things there are like Rust libraries. We use Rust SQLites, which is the Rust SQLites for interacting with SQL. We use Hyper because corrosion exposes like a HTTP API for writing and reading SQLite data. We also provide a Postgres endpoint. So yeah, we use Hyper and Axiom for the HTTP API. I think that most of it is built up. It uses like quick protocol instead of TCP, which is like this new protocol that has some advantages over TCP to within corrosion.
Then I was wondering about the name of the project, Corrosion. So now I know where it came from. It's built on Rust.
It's built on Rust, so it's just like a Rust name. I think it's a nice name, but when we've had issues where maybe there's an issue with corrosion and corrosion is like something rusted. It's not a good thing in real life. And someone is like, of course it has issues. It's called corrosion kind of thing. But yeah, I think it's a fun name. It's come to stick, definitely. But yeah, it's just following the line of a lot of Rust-based projects having Rust-based names.
Once you make the connection, it makes sense, right? So
yeah.
So also you talked about local first software. Is that updating local nodes first and then go to the global nodes? What is the concept?
Yeah, I think that's very close to that. It's basically the same thing. It's just, when I'm talking about nodes, it's like database, but I'll just give you examples of where CRDTs are used outside of storage systems. You still see them used within software, and it's very popular with the push to local first software, where people want to be able to use a software and still collaborate, right? So instead of every change has to go through a central server, once there's no internet, you can't access the software, you can't use it. And there's also, on the other hand, traditional software, like most desktop applications, where the application is completely available offline, but you can't collaborate across devices. You can't just move over your data because it's kind of stuck on one machine. So the local first software is kind of like an in-between between the both of them, where you do have the benefits of being able to use software locally, which means like access is quick, but also some of the benefits too of online software, of fully online software, where you're able to collaborate among multiple devices, and you do it in this way because whenever the application is ready or has access to network, in terms of maybe devices that disconnect from networks quickly and connect quickly, it can communicate with peers and send across data.
Yeah, that's cool. I think we can start wrapping up. Do you have any additional comments or any other thoughts before we close out today's discussion?
Oh yeah, I just realized I've talked a lot about CRDTs, but not actually about the CRDT that Corrosion itself uses. So Corrosion is built on top of SQLite, and we use an SQLite extension called CRSQL, which is just like a little spin on the name, like CRDTs and SQL joined together. So basically how CRSQL works is that this is an SQLite extension. So when Corrosion started up, it loads it into the database. Is that basically when you load the extension and you indicate which tables you want to merge as CRDTs, it would basically create like clock tables, these shadow tables, where it stores additional information for each of the rows, each column in each of the rows, right? So when you insert something like a data into a role in Corrosion, CRSQL creates metadata rows on these clock tables, and it tracks the node ID, which is the ID of the node where the data was originally written, the number of times the row has been deleted, recreated, or the number of times it's been updated too. So just information like that. And then these rows are actually what Corrosion communicates with a bunch of other nodes in the cluster. It would select rows from the clock tables and send out. So basically, SQLite has a lot of hooks. So before data is inserted, updated, or deleted in the SQLite table, it has hooks so that its code runs basically and inserts data into this table. What the merge looks like is that it checks first which columns. So it does it on a per column, not a per row base. So if you have a table that has one table and one row, like it has 3 columns on the table, it will create a row for each of those columns. So it tracks them at the columnar level. To merge it, it basically checks which of them has more updates, right? Whichever of them has been updated more frequently. He also tracks the deletes, right? So if one has been updated frequently but never deleted, the one that has been deleted and inserted a couple of times would win. But there's still going to be cases where these things don't work. So it still does a tiebreak on the value, which can be useful for numerical data. Then lastly, on the node ID, because each node has its own ID, so it does the last tiebreak. So it's actually fundamentally very simple. It has a very simple way, but also in the way that we use Corrosion is, there are times when there are conflicts, but it's also very useful in the system where there are different parts of things open data. So even though there's possibly conflicts, we know that most roles do not actually have a lot of things fighting over. It's really surprising what comes back from the database.
Do you have any additional comments in general in distributed data systems and networking areas?
There's a lot of stuff. I think where CRDTs become very interesting is when they're being used in like editing software like text, right? That's things become more complicated there because there's very granular stuff you have to track, the characters, where stuff is being inserted, where stuff is being deleted. And a lot of times CRDTs provide a way to resolve conflicts, but the application still has to decide, how does it send out the data? How does it synchronize states? So those are just actively interesting areas to me in how CRDTs are being used everywhere.
And definitely with the data being a little bit more textual and even other data types, we definitely have a lot of use cases. Somtochi, thank you very much for joining this podcast.
Thank you very much. Yeah, I've had so much fun. I feel like this is my first podcast. I was a bit anxious, but it's been very lovely talking to you. Thank you so much.
Yeah, it's great to discuss one of the important topics, right? Sometimes the CRDTs, the consistency doesn't get as much attention as you should.
Yes.
So definitely a good discussion. So, and for our listeners, thank you for listening to this podcast. If you would like to learn more about the data engineering topics, please check out the AI, ML, and data engineering community page on InfoQ.com website. I encourage you to listen to the recent podcasts. We're going to be publishing the AI, ML trends report very soon. So please check it out, and also other trend reports for architecture and agile and other areas. The InfoQ editors here who are also practitioners like you assess what's coming up in these areas, and we publish those trends reports. Thanks, Somtochi. Thank you.
Thank you.